It's gonna be all right. Hang in there. I love you. Oy. Which one? That's it, right? Okay. So. Alrighty, we got a few folks coming in. I see Ben is here. Today, Ben is going to teach us section 5.4, which is on indefinite integrals and the net change theorem. Ben and I went over his outline the other day and it looks great. You guys are in for a real treat. I'm curious, Ben, how did you decide to broadcast the lecture today?
I was going to screen share the notes that or like the lecture outline that I took. And then I'm going to interlap between a PDF of the notes and Paint 3D to write out some of the problems.
That sounds good. So what I'm going to do then is I will go ahead and make you a co-host. That will give you the ability to screen share. I think we're still waiting on a few people to arrive. So let's hold off until about 11:05. See if anybody else comes in here. But if you want to go ahead and get set up your screen share, do whatever you need to do. You can go ahead and get configured there. While you do that, I will grab some more coffee.
Sounds good.
Okay. Let's see, who are we still missing? Quite a few. Jonathan. Chris. Tahar and Kevin. Oh, no, Kevin's okay. All right. it looks like probably everybody who's going to be here today is now here. So Ben, you are now a co-host. I will let you take over and let's pay attention to Ben and learn a little bit about indefinite integrals.
Alrighty. Can you see the screen?
This looks good. Yep.
Okay, cool. So I guess I'll just dive right in it. So this section is 5.4 about indefinite integrals. So first, we can observe that both parts of the fundamental theorem of calculus establish connections between antiderivatives and definite integrals. So in part one, we have the integration of f of t from a to x, which is an antiderivative of f. And in part two, we see the integration of f of x from a to b is found when evaluating the antiderivative of f at b, which is the upper bound, minus the antiderivative of f of a, which is the lower bound, where f is the antiderivative or the antiderivative of f, or as seen here, which is just another notation for finding the antiderivative of a function. So the notation of indefinite integrals can be given by the integration of f of x dx, and you should never confuse an indefinite integral with definite integral, whereas the definite integrals will have, the bounds, upper bound, lower bound, and indefinite integrals will have no bounds. So another property that should be stated is that the integration of f of x dx is equal to the integral of f of x plus c, where c is the constant of integration and must be included to account for any arbitrary constant. Also, you can prove this answer by finding the derivative of the antiderivative, which should get you back to the original function. So as seen in this example, and I could work it out really quickly. So here in Paint 3D, if we have the integration of x cubed dx, this using the power rule, which I'll get to later, is equal to x to the fourth. Sorry, not this. The answer is equal to x to the fourth over 4 plus c. If you take the derivative of this, d over dx of x to the fourth over 4, c will just derive out as it's a constant. And that's also important to note that you must include c in every antiderivative answer because it can represent any constant of the previous function that is not necessarily accounted for in the in this proof. So the derivative of x to the fourth over 4 would just be equal to x cubed, arriving at our original answer. So now moving back into it, as explained, that there is a difference. And here, definite integrals will result in numbers, while indefinite integrals will result in an infinite family of functions. So as you'll find in the examples that of like the indefinite integrals, it will never result in a number answer. It will always result in a function answer, like tangent x, or as we saw at x to the fourth over 4, that's not a number answer, it's a function answer. While our practice with the definite integrals would always result in, a number fraction, we have the answer through the definite integral. Since it's bounded, we know the range that it's on. Also, as shown in the example, in Paint 3D, any answer can be confirmed by taking the derivative of the answer. So here we can see here the example, the antiderivative of secant squared x dx is equal to tan x plus c, since the derivative of tan x is equal to secant squared x. This is also found through a table that I'll later go over, and the table can be found by a series of proofs, but I think it's best to just commit the table to memory as it's faster. So as I just explained here, an important part of the indefinite integrals is the general table obtained from the various proofs that for some I like to call cycles. So here's an example of this table. The power rule, we know that derivative of sine x is cosine x, so the antiderivative of cosine x would just arrive us back at sine x. It's kind of like an inverse backwards operation of each other. So here it is important to note that this is used only because when we are given a function for an indefinite integral, we assume it is valid on an integral. So for example, if we have the integration of 1 over x squared dx, the antiderivative is negative 1 over x plus c. However, we have to confirm that as we know, the answer for x can't be 0, as the answer would be undefined. So we already know that the integral is valid from negative infinity to 0 and 0 to infinity. However, we don't need to implicitly state this. Here, another example, we have the integration of cosine theta over sine squared theta, d theta. We can simplify this before taking the derivative. So with indefinite integrals, a big part of solving, trig functions or even, polynomials, some of these functions get really nasty. And looking at it like face value, you wouldn't really necessarily know how to, solve the antiderivative of this without maybe some other property. So what you could do here is simplify the function. So we would get cosine theta over sine theta times 1 over sine theta, which is equivalent back to the original function. And here, this might look like something that we have on the table. So cosine theta over sine theta, which is be equal to cotangent theta. And I made a little error here. 1 over sine theta is cosecant theta. So now, after this simple simplification process, we have the integration of cotangent theta times cosecant theta d theta, which according to the table, which is right here, cosecant theta times cotangent theta would just be equal to negative cosecant theta. And that's what we get right here. So yeah, moving on into some of the more explicit rules, we have the power rule, the indefinite integral of a power function f of x equals x to the n, where n cannot equal -1, is the integration of x to the n dx is equal to 1 over n plus 1 times x to the power of n plus 1. So it's basically the function raised to its power plus 1 all over the power plus 1. And you obviously must include the arbitrary plus c value. So here we have an example, x to the 15. If we are finding the antiderivative of x to the 15th, we would just raise the function, which is x, to its power plus 1, which is 16, and divide the whole function by 16 and include the plus c value. Here again, we have the square root of x, which can be rewritten as x to the 1/2. So again, we'll have x to the 1/2 plus 1 all over 1 plus 1/2, which is equal to x to the 3/2 over 3/2, which you don't necessarily need to simplify, but if you wanted to, it would be 2x to the 3/2 all over 3, and then plus c. Here we have a sum and difference rule. So for integrable functions, f, we would have the integration of some function f of 1x plus or minus some other function f2x dx is equal to the integration of f of 1x dx plus or minus f of 2x dx. And you can arrive at this formula from simplifying like before, as seen with the cosine over sine squared. A lot of these require those intensive simplification steps to get to a function that, is not so ugly and, can be simplified into something like this, because this just makes the integration a lot easier. So here we have an example of the integration of 5x plus 7 dx. So this could be spread out into the integration of 5x dx plus the integration of 7 dx. Here we'll go into later of a coefficient rule. So the coefficient of the function can move out of the integration, but it would be multiplied by the answer of the integration. So 5 times the integration of x would still be equal to the integration of 5x. And here we have a constant function, which is just 7. And whenever you have a constant function, the integration was just going to be adding an x to it, or whatever variable you're using. So here we have 5 times the integration of x, which is just 1/2 x squared, 1/2 times x squared, since x is technically x to the power of 1. So it'd be x plus x to the 1 plus 1 all over 1 plus 1, which is where we would get the x squared over 2 plus c1, and I'll get to this later. And then that's the answer for the first integration. The next integral, we have 7x, as explained with the constant rule, by just adding the x. So when you're doing this, C1 and C2 are individual, but are the same technically. They're both arbitrary constant values. So it doesn't necessarily matter since you're not going to be finding C1 or C2. So in the answer, you always write just plus C instead of plus C1 and plus C2, as C is just any arbitrary constant function. And after distributing the 5 into the 1 over x squared, or 1 over 2x squared, you get 5 over 2x squared plus the 7x constant function. So here are the two rules that we just used in those examples. The constant rule of k is any real number, then the indefinite integral of k with respect to x would just be the integration of k times k dx, which is equal to kx plus c. And the coefficient rule, given any real number coefficient a and integrable function f, the integration of a times f of x dx is just equal to a times the integration of f of x dx. So here I wanted to move into some more examples using all of these rules. So here we have the integration of quantity dx to the fourth minus 9x squared minus the square root of x dx. So the first thing that we could do is split the function using the sum and difference rule and make it more simple to integrate. So once we split using the sum and difference rule, we would have the integration of 6x to the fourth dx minus the integration of 9x squared dx minus the integration of x to the 1/2, which is equivalent to square root of x dx. Now this looks like something that we can start taking the derivative of, but again, we can simplify here using the coefficient rule. So we can move 6 out, so it would be 6 times the integration of x to the fourth dx minus 9 times the integration of x to the x squared dx. And since there's no 1 is just the coefficient, we wouldn't move anything out. And it's also important to know that using the order of operations, we would do multiplication here first before maybe subtracting 6 minus 9. So you don't want to make the error of subtracting 6 minus 9 and then multiplying. Then we can move into the integration step. So here I kind of skipped a step, but the integration of x to the fourth would just be x to the fifth over 5. The integration of using the power rule, the integration of x squared would just be x to the third over 3. And then the integration of this would just be x to the 1/2 plus 1, which is x to the 3 over 2, all over 3 over 2. And then we can distribute each coefficient. So as we found, it would be x to the fifth over 5. And if you multiply by 6, you'll get 6 over 5 times x to the fifth minus 9 over 3, which would simplify to 3x cubed, and then minus 2 over 3x to the 3 over 2 plus, and then plus c. And here, I think I went over an example using a square root earlier. So here's that simplification in an answer. So moving into another example, here we have the integration of 8x cubed plus 4 all over x to the 7 over 3. So what we could do here is split the function, since this is technically 8x cubed over x to the 7 over 3 plus 4 over x to the 7 over 3. And we can bring up this power into the numerator. So we would get 8x cubed times x to the negative 7 over 3 dx plus the integration of 4x to the negative 7 over 3 dx. And now again, this is looking like something that we can start taking the integration of. However, first you'd want to simplify. So x cubed times x to the negative 7 over 3. You just add the powers and you would get x to the 2 over 3 dx. Take out the 8 using the coefficient rule. You had 8 times the integration of x to the 2 over 3 dx plus 4 times the integration of x to the negative 7 over 3. Again, using the coefficient rule here. Then we move into the actual integral part. So here, x to the 2 over 3, the integration of this, you would use the power rule. So you would just add 1 to 2 over 3 and divide the whole function by 2 over 3 plus 1. And basically the same thing in this integration, x to the negative 7 over 3 plus 1 all over negative 7 over 3 plus 1. And then finally, you would multiply each fraction by its previous coefficient. So then you would get something that looks like this. And you can simplify by moving the 3 up and getting 24x to the 5 over 3 over 5. And here again, 12x the negative 4 over 3 over negative 4, which you could simplify by dividing 12 over 4. But I mean, both answers are equivalent. So I'm using an example with trig values. Again, we're going to have to refer to the table if you haven't committed it to memory. So here we have the integration of 3 cosecant x times cotangent x minus 7 secant squared x dx. Now it's important to know that we can use the sum and difference rule here. However, we cannot split cosecant x and cotangent x since they're being multiplied. You can split 3 cosecant x cotangent x from the negative 7 secant squared x, but you can't split these two. So you have to be careful when you're applying these separate individual rules. So as I just explained here, we can split these two, which is what we'll get here. And then we can apply the coefficient rule by taking the 3 out and taking the 7 out. And then we can evaluate each integral using the table, which makes it extremely easy. So we'll get the negative cosecant x plus c1 minus the tan x plus c2. And as I previously explained with the arbitrary c functions, c values, c1 and c2 are different but the same. They both just use c in the answer. You don't need to individualize c1 and c2. So here is from the chart. Here, I can scroll up really quickly. Here we have the chart of each answer. So the integration of secant squared x is just tan x. And I think it was cosecant and cotangent, which is negative cosecant x plus c. So now I just got to find this again. So yeah, so here are the answers. Now you just distribute this coefficient and you'll get negative 3 cosecant x minus 7 tan x plus the one arbitrary c value. I think one last example. As you can see, these indefinite integrals can get pretty disgusting pretty quickly. So it requires a lot of algebra skills in the simplification of each function. I think it's also important to note that the importance of the integral chart, because you can simplify past the values that we see on the integral chart. So if you have the integral chart committed to memory, let's say, as we saw here, we have the cosecant cotangent. In some examples, you can simplify past the cosecant x times the cotangent x into something that's even simpler, but isn't on the chart, which makes that integration extremely difficult. So you have to be really careful and really versed while taking the integration of a function and know where to stop and whether or not you need to keep going to simplify. So making an account of that, moving into this function, we have 3 tan theta minus 4 cosecant squared theta all over the cosine squared theta all over cosine theta d theta. So the first thing you want to do is we can split up the function. So we can have 3 tan theta over cosine theta d theta minus the 4 cosine squared theta over cosine theta. So the first part of the function could simplify into 1 over cosine theta times tan theta, which 1 over cosine theta would just be secant theta times the tangent theta. Here, for cosine squared theta over cosine theta, it's just 4 cosine theta. Applying the coefficient rule, we can take the 3 out and the 4 out. So we'll have 3 times the integration of 1 over cosine theta times tangent of theta d theta minus 4 times the integration of cosine theta d theta. And now here we have something that looks like something that we can find on the chart. So here we'll have the secant theta times the tangent theta minus the cosine theta d theta. So now using the chart, we'll get here secant theta minus the sine theta plus c. And then you have to distribute your coefficients. So you get 3 secant theta minus 4 sine theta plus c. So also I want to transition back into Paint 3D because I think this is pretty cool using the sine and cosine trig values. So if we're the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. And the derivative of negative sine x is negative cosine x. And if you take the derivative of negative cosine x, you'll arrive back at what you started with sine x. What I think is cool about this function is that I like to think of this as a cycle, and you can use this in antiderivatives. So the antiderivatives would just be the other way around. So as we see, derivatives kind of move down and then go back up. You can use the antiderivatives in the other way. So let's say if you wanted to start with negative cosine x, the antiderivative would be negative sine x, and obviously plus c. But here, just for like simplification's sake, we'll just write it like this. If you wanted to start with, and then if you take the derivative of, or antiderivative of negative sine x, you get cosine x. And then if you take the antiderivative of cosine x, you get sine x. So I think only one of these is written on the table. And I'm pretty sure it's just the derivative of sine x, cosine x, and the antiderivative of cosine x is sine x. You can use this little cycle to really find the antiderivative of any sine or cosine function. So that was also like tying back into the proofs that I discussed earlier. So now we can move into applications of the indefinite integral. So the fundamental theorem of calculus says that if f is continuous on a to b, then the integration from a to b of f of x dx will be equal to the antiderivative of f at b minus the antiderivative of f at a, where f is any derivative, or where the antiderivative of f is any derivative of f. This means that the derivative of the antiderivative is equal to f, which can
Just
be
for
written.
clarity here, I'm sorry, I want to jump in for 1 second. So capital F here is any antiderivative of little f, right? I think we need an anti in front of the word derivative there.
Yeah. Well, like, because this was already the antiderivative.
Right, yeah. So this is integral a to b of little f of x dx equals capital F of b minus capital F of a, where capital F is any antiderivative of little f.
Yeah.
All right, yeah, everything else is good.
All right, yeah, sorry about that. And then here we can move into where the proof or integration from a to b of the any antiderivative, or the derivative of any antiderivative of x dx would be equal to what we discussed earlier, where any antiderivative of the function at b minus any antiderivative of the function at a.
So the idea here, I'm sorry, I'm going to jump in just one more time. The idea here is that if you integrate f primed, you'll get f, right? F is an antiderivative for f primed. So the integral of f primed from a to b is f of b minus f of a. So if you're looking at this formula, that's at the sort of top of the page now. So the second integral formula, yeah, the one where his mouse is there, that's a capital F primed inside the integral, and these are capital F's out here. So the idea is the integral of f primed is f of b minus f of a. So the f's on this second formula line where the cursor is now are all capital. So the integral from a to b of cap f primed is cap f of b minus cap f of a. And this is just a restatement of FTC, right? Little f is cap f primed in the first integral formula up there. So we're just replacing little f by cap f primed. And it helps you see a little bit the connection between the integral of a derivative and the integral of the values of the actual function. Everything there is correct. I just wanted to emphasize that these two lines, the two integral formulas, really say the same thing.
So this would show that the cap f primed of x represents the rate of change of y equals cap f of x, with respect to x. And the cap f of b minus cap f of a is the change in y when x changes from a to b. So you can also use indefinite integrals as well as definite integrals in rate of change problems and kinematic problems, which I'll get into later. And then, so here we can show the net change theorem, which is the integration from a to b of cap f primed of x dx is equal to cap f of b minus cap f of a, which is derived from the fundamental theorem of calculus. So here, if we have an example, if V of t is volume of water in a reservoir at the time t, then its derivative, V prime of t, is the rate of change, a rate at which water flows into the reservoir at time t. So the antiderivative from t2 to t1 of V primed of t dt is equal to the capital V of t2 minus the cap V of T1, which we can derive from this integral. So this is the change in the amount of water in the reservoir between time 1 and time 2. And this can be applied to any rate of change problem. So here we can also use it in kinematics with a kinematics problem. So a particle moves along a line so that its velocity can be modeled by V of t is equal to t squared minus 5t minus 4. And we can find the displacement from a given interval. And we can also find the distance traveled. So here it's also important to note that, that there's a difference between displacement and distance. And that is if traveling in one direction and then another, velocity can be positive or negative. So the net change in displacement won't be the same as the distance, because displacement is from the velocity. And as stated, the velocity can either be negative or positive, while distance, can't really be negative. So here we can find the displacement by deriving that s of 4 minus s of 1 is equal to the integration from 1 to 4 of vt, which is t squared minus 5t minus 4. So here we take the integration using the power rules. You get t cubed over 3 minus 5t squared over 2 minus 4t. And we would evaluate at the points at the different values. So first it would be the upper bound, so v of b, minus the lower bound, so v of a. So it would be, you plug in 4, which is the b value. You'd get into the antiderivative function. So you'd get, this minus, once plugging in 1, you get this, and this would simplify to negative 57 over 2. This is also important to note that depending on the kinematics problem, negative 57 over 2 is the negative part is just signifying which direction it's moving in. So most of these kinematic problems will either move right to left or up or down. So this would just mean that the particle is moving to the left instead of to the right. Its speed is still, 57 over 2, or that at least the displacement is right now, but it's just moving. It's not negative 57 over 2. Speed can't be negative. It's just the direction it's moving in. So then here we see that, as seen, indefinite integrals are a major component of calculus and can be used individually as well as in conjunction with definite integrals. So I also wanted to point out that you can find the distance traveled. I chose a really poor function for this. This can't be factored. And in order to find the distance, you need to factor the original function. So you'll get some really irrational roots from this. And what you would do is you would evaluate the individual roots from the number line from the range that's given. So 1 is less than or equal to t, which is less than or equal to 4. So for example, if we got t minus 3, t minus 2, for example, or t plus 2, we would have t is equal to 3 and t is equal to negative 2. So negative 2 is not valid on this interval, so we'd use 3. So all you would have to do is find the integration at the 3 value. So it'd be 1 to 3 and then 3 to 4. So you would evaluate 2 different integral functions. I just chose a really poor function, and it's really hard to find the distance with rational roots. So for the rest of this, I wanted to jump into examples that I have to maybe like make it kind of easier to talk it out while I'm doing it and what I'm necessarily thinking about when I'm evaluating something like an integration function. So let's say we have integration from at sine x all over cosine squared x dx. Before diving into the antiderivative of the function, I want to simplify. So I can simplify this by writing sine x over cosine x times 1 over cosine x. So that's equal to the original function. And then this could be rewritten as tan of x times secant of x dx. So I ran out of space there. And using the integral table that I have in my head, we know that the integration of this will be equal to secant of x plus c. So another one that we could do, I mean, that's just showing the importance of the simplification, because evaluating sine x over cosine squared x without simplifying it, it's pretty hard, I'd say, without the simplification process. But once you kind of get it into its bread and butter form, it's pretty easy, and it kind of every indefinite integral, at least right now, will line up with the chart. So here we can use another example, which I think can be the last one, which is x plus 5, let's say, times 2x minus 3 dx. So what I would want to do before evaluating this is distribute. So get it into its longer polynomial instead of factored version. So that would be 2x squared minus 3x plus 10x minus 15 dx, and always include the quantity. And then we could simplify these two, since there's like terms, into 2x squared plus 7x minus 15. And so here now, using the rules that we've found, we can make this sum and difference. So we could have 2x squared plus x minus the integration of 15 dx. And you have to include dx's for each integral. So here we can find, using the power rule, that the answer is just going to be 2 times x cubed all over 3 plus 7x squared all over 2 minus 15x using the constant rule plus c. So that is about it that I have. I guess if there's any questions, I can answer them.
All right, I see that we did get a handful of people drifting in a little bit late. So let's start by thanking Ben for the work that he did here. And then are there any particular problems that you guys wanted to look at more closely? Or is there anywhere you guys were unable to get complete notes there that you'd like to go back and look at in more detail? Anything like that? Okay. I do see some gratitude being expressed in the chat. That's very nice. I don't see any explicit questions, and my intent for Friday is to come back and solve a few more kinematics problems. Let me turn on my video. Come back, excuse me, on Friday and solve a few more kinematics problems that make use of this sort of thing. I would like to give you guys a few moments to look at one. Well, actually, we could do that on Friday also, because we are a little bit ahead of time. So we can go ahead and wrap it up here if there aren't any questions. Yeah, the things that I might insert here are things that I am going to do with you guys on Friday anyhow. So it's okay. It's so hard to like go slow enough. That's always the struggle, is to like pace things for those who are writing, because it's so simple. It's so easy to get nervous. It's such a natural thing to do and to want to move fast. But you did a wonderful job here, Ben. I think everything that needed to be communicated was communicated, and effectively so. So we'll go ahead and end it here. That's okay. You guys can have a slightly shorter day today. I'll get the recording, of course, posted for anybody who wants to review it. And then on Friday, we're going to look at a handful of problems coming from this section. There are a few fun things that we can talk about while we're here. So the difference between displacement and distance, especially in these kinematics problems, are fascinating. We know that the integral measures, let me turn this on. We know that the integral measures signed area normally. So if you just integrate v of t, if your velocity function is sometimes negative and sometimes positive, then these pieces would be measuring distance. But this guy is going to come out negative. So he's not going to give you the contribution to your distance integral that you want. So the kind of fundamental thing you need to remember for those kinematics problems is that the integral of velocity gives you your displacement, which is how far you end up from where you started. Which is not the same thing as distance, because if I walk to the grocery store and then back from the grocery store, my total displacement is 0. I ended where I started, but my total distance is certainly not 0. And that corresponds to this picture here, where your velocity is positive, you're walking away, and this would be the distance you walked away. But then your velocity is negative, so you're walking back towards home. So this would be the distance you walked back towards home. And then this is you walking away again. So your overall displacement here is going to be different from your overall distance, because this is going to kind of subtract out from the distance rather than adding to it. There are ways to fix this, namely by integrating the absolute value of your velocity instead. And because I didn't get to do any examples like that with my class this morning, my non-honors class, we just got to this place. I would be happy to run through some examples of this nature with you guys on Friday. So that is my plan for now. I think we have covered all of the basics we need for indefinite integrals, which is good. It's not anything too crazy. It really is just notation, right? So the indefinite integral stands for the most general antiderivative of the function inside. One thing I would recommend everybody take a look at page 403 in the textbook and make sure this table, well, maybe with the exception of these bottom two guys, we don't really stress about the hyperbolic functions that much, but make sure that this table gets into your notes. Make sure that you are very comfortable with these things. The remainder of the semester, and indeed the first half of Calc 2, is all about integration. And these things are the absolute basics, like the very foundation of the integration skills. You need to have these, not just in your notes, in your brain. They need to be rock solid in your brain. So start by getting these into your notes. And then as you work through the homework, of course, you'll get more and more comfortable with the antiderivative process. Your most powerful tool there, like Ben said, is algebra, right? Just being able to rewrite those integrands, those functions, in a way that you can then apply this table of known integrals. So, well, yeah, it's possible to simplify some things like this into other expressions. We want to get to a place where we have the habits and the algebra skills that will allow us to simplify them into pieces that we can recognize from our antiderivative table, our known antiderivatives, our known integrals. One last thing I'd like to share with you before we go. Where is it? Let's see. a little joke. Comparing differentiation to integration. XKCD, by the way, if you're not familiar with this webcomic, it is the best of the nerdy webcomics. Saturday Morning Breakfast Cereal is good. The grad school one is good, but XKCD is really the way to go if you want a quick giggle of a mathematical or scientific flavor. This particular one is about differentiation compared to integration. So when you're differentiating a function, you start, apply one of the rules, and if you're done, you are done. If you're not done, then it just means you need to chain rule and do a little bit more. Integration is a very different matter. You try applying some of these things. We haven't even talked about these yet, but we will learn substitution in this class. And then are you done? Haha, nope, question mark, Cauchy's formula, question mark, Riemann integration, question mark, partial fractions, install Mathematica, Stokes theorem, Risch algorithm. What the hell is a Bessel function? Phone calls to mathematicians. Oh shit, burn the evidence. So integration is indeed a little bit more challenging. There are many functions that nobody can integrate. In fact, there's been some time put into proving that certain functions just don't have antiderivatives that can be written down in a finite length expression. And if you come see me in Calc 2, I'll show you how to handle those with infinite length expressions, they're called power series, and how to handle all of these crazy little things. So integration is more challenging than differentiation, and we need to treat it like that. So this bedrock, this foundation, needs to be very solid. You need to know these things immediately. And then the algebra skills to simplify slightly more complex things into these things also is bedrock, needs to be rock solid. So take this week's homework quite seriously, and it will pay off down the road. On Friday, I'm going to look a little bit more deeply at some of these kinematics problems, and then we're going to be ready to start talking about substitution next week. So next week, we will talk about section 5.5, which is on the substitution rule. And then after that, we'll be moving into chapter 6. There's just a little bit from chapter 6 that we do on areas between curves, and that will be the end of the class. So we're very close. The end is near in a good way. And that's where we're going. So thank you again, Ben, for the work you put into the presentation. I think it was very nice. And Friday, we'll look at some more application problems, and then we'll start moving on to substitution. Any questions for Ben or myself before we get moving? Alrighty then, I'll go ahead and end the meeting here. I do have my normal office hour today from 1 to 2 p.m. If you guys want to come talk about anything, or if you have any questions, I will be there. Otherwise, I will see everybody on Friday. Bye, guys.